I am a lighting designer, architectural lighting designer, and the company I work for is called Francis Krahe and Associates. Our Ohio branch is somewhat new, just 2.5 years, but we've been around since 1983. So our headquarters is in Los Angeles. I used to be in the Los Angeles office. So here in Cleveland, we're in the Murray Hill building, and I put that picture up because it's kind of interesting. In Los Angeles, we're in the Bradbury building, which is an historical building, very cool. It was in Blade Runner, if anybody saw that movie. So yeah, I have been, let's see, in architectural lighting, like over 20 years now. So I love lighting, I love architecture. And also the subject of lighting and health has always been an interest of mine. And you'll see, in sort of the general public, it's becoming more of a known topic. So, but personally, it's been an interest of mine for many years. So now in this talk, we'll be kind of going through like lots of metrics and standards, recommendations, but I kind of want to note that I myself, I don't believe that, everything related to wellness can necessarily be measured. However, we do, as design professionals, need some kind of common language around that, and also some kind of scientific basis that we kind of draw our evidence on and integrate into our design. So yeah, so I like to think of, the design of space as lots of rhythms, and lighting is yet another kind of rhythm, as we know the daylight changes. So it's another layer on within our perception of space, or actually we wouldn't be able to perceive the space without lighting. But anyway, so as far as designers, we do have an ability to really kind of influence how people feel. And for me, I think that's, kind of an honor to be able to have that type of impact on how people feel. And the other thing about designing space, and the more I get into it and learn kind of the science behind it, you could see how the eye is really just, at the back of the eye, it's just brain tissue. So it's our visual system, the back of our optic nerve connects to the brain. And it's really an extension of the brain, right? So we see with the brain, not just our eyeballs, right? So for me, that's kind of an exciting thing. And I'm also somewhat of a neuroscience fan, although I'm not a neuroscientist myself. So what are we going to talk about? So this is a big subject, obviously, so I have to kind of break it down. So we're going to talk about light's effect on the body in a more physiological sense, and kind of the background of what happens. And then we'll talk a little bit about color science. And I'm not going to go too deep into that because it's quite a big subject, but it relates to this idea of circadian lighting. So, and then I'll touch on WELL. And I just 2 months ago got WELL AP, and there's a big section on lighting. And I'll talk a little bit about daylighting analysis, and also some of the software tools that we're using, which are useful for not just lighting designers, but for architects as well. So So yeah, we'll talk about light's effect on the body, but I just wanted to mention that an interest of mine is not only kind of how light affects our sleep-wake cycle, but also how light affects our kind of psychological wellness. So that is a subject I'm doing research now, and I'm not really going to go into it on this talk, but just stay tuned. Later in 2021, I'll kind of have this research together, and I'll be giving a talk at a big conference in New York at the end of October about light and sort of the mind. So, but the reason why I wanted to bring this up to architects is because you may be interested in this idea of neuroaesthetics. So it has to do with psychology, neuroscience, and our human evolution. And there are people that are really deeply going into this topic. And I will be interviewing a number of people that are specialists in neuroscience for architecture. So anyway, so later in 2021, I'll be kind of synthesizing some of this research. But in case you're interested in the topic, I would go to the Center for Conscious Design. So it's really fascinating, and they're using all sorts of sensors and such to kind of, you know, take this out of just a lofty idea, but actually measuring certain ways of how our neurological systems experience architecture. So it's really fascinating, but that's not what this talk about. But the reason I bring it up is because when we talk about wellness, we can't separate, you know, the body from the mind necessarily, right? So, but in this talk, I am going to really talk about how literally light affects our sleep-wake cycle. And the National Institute of General Medicine, so the way they describe, so what is circadian rhythm? So circadian rhythm is really about that 24-hour cycle we have in our bodies, right? And the biggest sort of influencer on what this cycle is, the signal that tells you, you know, you get sleepy or not get sleepy, is light. So our bodies respond to light and darkness. And in our eye, we have, you know, the visual system, and the visual cortex is actually like where the images are formed, is kind of in the back of the brain. And we've known this for a long time. So there's rods and cones. Cones detect color. So this is really something you probably learned in school as a kid in biology. And then later in, you know, in the 2000s, they discovered another cell in the back of the eye called the intrinsically photosensitive retinal ganglion cell, and the IPRGC. So this is a protein in the back of the eye that detects light, but not to our visual system. So it's actually detecting light and sending signals to another part of the brain, the center of the brain, which regulates hormone secretion and our sleep-wake cycle. So we're taking light into our eyes, but it's not just for image forming. And they discovered this not that long ago, right? So this cell tells us a lot more about how light affects, you know, sleep disorders, seasonal affective disorder, right? That's kind of like when you feel kind of blue in the winter, right? Less light, right? Mood disorders, migraines. So these are related to light, right? And I think a lot of people know this intuitively, right? But now scientists are really able to kind of base research and studies on this, but I think everybody kind of knows this intuitively. So entrainment is how our bodies get synchronized, right? to this sleep-wake cycle. So light is the most powerful external cue for entrainment. So in this image, that's a project actually that was recently completed in Los Angeles, and it's a kind of, not really a spa, it's kind of a skin treatment center. And there's lots of rooms that are windowless, so we really kind of go out of our way to provide light in those windowless environments. And we also think about how light comes in from other directions, not just from above. So light from the side, light from below, and that's kind of also for aesthetics, but also how I mentioned how light enters our eye. So here is a little diagram. You have the visual cortex, so that's your visual system, light coming in. And then you have light coming in and hitting the back of your eye, sending a signal to your pineal gland, right? And that has to do with hormone secretion. And one of the hormones is melanopsin, so which has to do with getting sleepy. So you have melatonin and cortisol. So melatonin is in your body when you're sleepy. That's what you want to be at night. And cortisol is telling you to wake up. So ideally, you want these to be like this chart: high melatonin at night, high cortisol in the day. So that's a healthy kind of system, right? So different wavelengths of light activate this system of melatonin suppression or secretion. So they found that 460 to 490 nanometers actually is the most sensitive to tell you to make you alert. Now, this is, you may have heard of tunable systems related to circadian lighting. So this is what this has to do with: regulating the spectrum of the light so that it activates your circadian system. And this is important, the certain color of the light, but the thing that's more important is the amount of light. So just in a nutshell, to have a healthy system, you want bright light earlier in the day, right, between 9 and noon. And then you want it to be darker as the day progresses. So late at night, like after work, when you go home, try not to turn on all your lights, and particularly before bed, right? Don't look at very bright sources, dim your lights, right? So that's kind of the general guidance. But then in the day, you want to get some light. So really an easy way is to go for a walk at lunchtime. But even in the day when you're having lunch, you know, try to sit near a window, or if you're not where you're, like wherever you are eating lunch, make an effort to have that time where actually light is hitting your eye, right? So, and why is sleep so important? So when I was a teenager, you know, you don't care. You're like, why do I need sleep, or when? But actually sleep, I think everybody knows, if you had a good night's sleep, you are in a better mood in the morning, you know, because sleep literally cleans up your brain. So you have stress hormones that have been secreted into the body, and when you sleep, they're literally cleaning those out, right? So that's what happens when you're sleeping. It's cleaning up these chemicals in your brain. So a bit about color science, I put 0.101 instead of 101 because, again, this is a big subject, but, and this is color science is relating to white light. So we have here, this is a color chart, and this line here is what we would call white light, right? It's on this thing they call the black body curve. So you may have heard of warm color temperature, cool color temperature. So on this line, you have 10,000 here, so that's a cooler temperature. And warmer would be 2,000, the lower numbers, right? So you might have heard that 3,000 K, 4,000 K. So that has to do with light being warm or cool. However, that doesn't tell you the whole story about what is comprised in that white light source. So you see on these other axes different curves. So this color model, okay, you're talking about the warmth and the coolness, but the other part of white light is that it has different wavelengths comprised within that white light. So I like to think of it as like a recipe, right? So you have tomato soup, and there's all different ways to make that tomato soup. So, and that is with the spectral power distribution. So I think we all know intuitively, right? Fluorescent light somehow doesn't feel great, right? It's not a continuous spectrum, right? So this is an artificial light source, all of these here, except for daylight, right? And it doesn't have all the colors of the spectrum. So it's white, but again, within the recipe, it has less ingredients, you could say. Daylight is how our bodies are attuned the most as humans, right? So it's a full spectrum. So that is kind of, this tells you here kind of the recipe which is in a light source. And when I was talking about 460 nanometers, that's somewhere around here, right? So incandescent has less in that spectrum. So, so that is kind of what's within a light source. But my tip in terms of color tunable lighting, right? I'm not talking about color for accenting blue, red, but within white light, it's important, but what's more important is the amount of light, right? And at the certain time of the day. So again, here is a little chart that shows you light comes into the brain and into the eye, and this part of the brain, it sends signals, right? Melatonin, suppress it, or produce melatonin, right? Get sleepy. So these are little signals that are going on. So the bluer kind of 460 nanometers is telling you to suppress the melatonin, and then the warmer kind of 630 nanometers is telling you to sort of get sleepy. So you've seen on the iPhone, they have that amber, that setting where the amber light comes on. That is because it's blocking out the 460 nanometers. So that is why they have that. So to help you sleep at night. So I'm not going to go into this too deeply because it's definitely very dense, but I'll just explain the concept. So you have, the way we measure light is photopic, scotopic, and mesoptic. And that's because our eye kind of operates, it's more sensitive to certain wavelengths depending on the amount of light. So that's it in a nutshell, but what we need to know about this is that when you see a light fixture, the data that comes out of it, whether the foot candles that you measure using that light source information, the lumens, are measured for normal lighting conditions for photopic. So, but don't worry too deeply about that. So this is an image here. We do lots of lighting calculations, right? So back in the day, we did them by hand. I mean, that was like a long time ago. We do them on computers now. And not only the great thing now is you could take your whole model and just use the model and calculate in there. So you see a rendering here, but it's not, it's a rendering, but it's actually a calculation. These are images that are output from calculation software that we use. And then on the right here is what we call pseudo color, and each color represents amount of foot candles falling on surfaces. So this is just a representative, but all of these are measured in photopic lumens. And that is when we do foot candle measurements. But again, that is for the visual system, not for the non-visual system. So again, we're talking about light here in the non-visual sense, but I just wanted to kind of make that distinction. They are related, but these calculations show photopic lumens in the visual system. So all of these calculations, basically, you can slice them in whatever plane and get data. So really, you're looking at renderings, but they're really just a bunch of numbers, right? So wherever you slice the calculation plane, right? That's a readout of numbers, light levels. So, so I wanted to touch briefly about some research, and some of it related to what could be interest to lighting designer, to architects. And I talk to a lot of people, and I attend a lot of scientific seminars related to light and health. And I even got to interview some folks at the General Services Administration. So, so I'll get to that, but somebody asked about WELL. So some of you may know more about it. Some of you may know less, but basically it is a building standard that LEED has to do with more of energy efficiency and environmental impact. WELL has to do more with how humans, their kind of experience in the building, right? So very much like human-centric, right? And light is a big part of that standard. So certain buildings are going after WELL. You'll see that more and more, just like LEED. When LEED first came out, it was less buildings. Now there's many, many buildings, but you'll see WELL. And the light section, like I said, is a pretty big part of it. And there are certain prerequisites, and then there's certain kind of optimizations that are similar to LEED. So light has, you see 9 parts here. And I'm not going to go through all of them, but I kind of want to explain more of the principles behind them, because each one is, kind of technical, but I just want to give you kind of the basic outline. So light exposure, which is a prerequisite, has to do with things that really not necessarily, okay, are they're daylight, a lot of them are daylight related. So spatial daylight autonomy has to do with the amount of daylight in certain, and the measurement of the area within the building. That's also in LEED. So that is part of that light exposure. And that has references to daylight metrics that the Illuminating Engineering Society, or IES, publishes. So again, I'm not going to go into what that is, but these are all daylighting metrics. So as a company, we also do daylighting consulting. So spatial daylight autonomy is part of the prerequisites, right? And some of that, however, does not have to be modeled. That's one way to do it, to do a model. And then the other way is really just to measure how much glazing you have. And in that part, you don't really need a daylight consultant, right? Architects could do that part. So light exposure, there's different ways to get to that prerequisite, but one of them is calculating spatial daylight autonomy, and later I'll talk about tools of how to do that. And the other one is literally just kind of quantifying the glazing. So, and then the prerequisite here is an option for circadian lighting design, which I am going to talk about. You achieve 1 point in, so it's a prerequisite, but your prerequisite can be achieved by getting a point in an optimization. So the other prerequisite, so these are meaning things you have to do if you want to get well, is in a point called visual lighting design. And basically, as lighting designers, we do that anyway. Basically, they're saying, design your lighting to certain design standards. That's what they're saying at this point. So the IES Lighting Handbook publishes certain recommendations for certain type of spaces and certain ratios of brightness, etc. So basically, they're telling you in this prerequisite is to do intentional lighting design, right? So, but you do have to verify it. So that's part of this prerequisite. And then they go in and they actually do a performance test. So if you say my lab building has this amount of lighting on the lab benches, they'll go in and, you know, measure it later. So they do, there's lots of well points that they go in and do a performance test. So, so then the other part, which I'll talk a little bit deeper into, relates to the whole beginning part of my talk, which was about light and the body. And in this point, it's an optimization. So it says meet lighting for day active people. So pretty much it doesn't really go into like, okay, how do you light for night workers and such. It's really for day active people. And it says here, at least 150 EML. So you're like, gee whiz, what's an EML? So that is equivalent melanopic lux, okay? So you might have heard of foot candles or lux, right? The amount of light falling on a surface, right? That is more perhaps familiar to people. That has to do with the amount of visual light. Now, melanopic lux has to do with the amount of light as weighted for our circadian system. So, and I'll show you a little bit more what that means. So EML, equivalent melanopic lux. So the other way that and these are all new, these terms actually, these metrics. So the other thing, you have melanopic lux, EML, and then another way to measure it, which Well Building Institute recognizes, is circadian stimulus, or CS. So right here, so there's levels of that CS. So these are two metrics, and the reason why there's two metrics is because there's different research bodies that have come out with this research. So Well Building Institute kind of recognizes both of the types of research related to circadian lighting. So again, melanopic lux has to do with light and the non-visual system. And if you just say lux, right, without the melanopic, that has to do with the visual system. Okay, so here is an example, and it's a pretty simple example. You know, it's perhaps something that you could think about in some of your projects. So it's going into construction now. We designed lighting for at West Virginia University, brand new building for their business and economics school. So big building in West Virginia. So there is a series of offices that are on the edges of the building, on the perimeter. And there are a series of offices that are interior, right? So you have offices with windows and offices without windows. And, you know, as we design, you know, we think, okay, we'll do this way, this way. But I always like to, you know, I want to think about, well, who's the person? They have to exist in that space for all day, you know? So we, as lighting designers, always intuitively kind of go out of our way to design lighting, you know, in a little bit more considerate way for rooms that don't have windows, right? We knew this intuitively, and now with all this research with our bodies and circadian system, we know that there are other reasons that this affects our sleep-wake cycle. So I'll show you here. So this building did not get well certified, but I kind of used it as a test bed for circadian lighting, and it's still in, you know, just going into construction. So once it's built, I can go in and do the measurements. But so you have an office with a window and an office without. And so the office with the window, we have an up-down pendant, different, and you can modulate. And then in the office without the window, we have a shorter length of pendant, but we have a continuous wall cove. So this back wall, there is no window, is completely washed with light, and it's also bouncing off that wall and sending light sort of towards your face, right? So it feels good because you have this vertical surface that has light on it, and then also you have light that's hitting your eye. And so here you can see office with the window, and then this continuous wall cove here, right? So here's the person at their desk, and in well, this little spot here would kind of be, this is where you measure the melanopic lux, where their eye is. So the amount of light, melanopic lux, that's hitting your eye here, of someone sitting there. So this light bouncing will contribute to that. Now the person with the window, the daylight is, right? But this person doesn't have that, right? So this wall cove really is important, instead of just having the pendant over their head. So again, in well, I just put that up there. They'll come in and they'll do a measurement of this and check it out. So in this sample, we met the threshold. We had 161 EML. And the way we came to that is we had our light source, which is, you know, 3000 K. But again, all 3000 K are not the same. They have different spectral content. And that has a weighting ratio, which which affects how much of the circadian system is activated, right? So we took our photopic lux and our certain spectral content, and we were able to get kind of the ratio of how much melanopic lux we would get. So this gets a little complicated, so you may, you know, your brain might be spinning, but that's what we did here. And it actually, there's tools online that you can plug these into, but I just wanted to give you the background of what that is, right? So basically we measured this melanopic lux at this point where this person's eyeball would be. So that's a simple application. So of getting light onto someone's face, right? And this is just a little device here. I have one of these. It not only measures light, but it measures the spectral content. It measures flicker. It measures all of these other aspects of light that relate to health. And I won't really go into flicker in this talk, but that's another optimization for well to have a certain thresholds that you meet of the flicker of the light. So I won't go into that too much. So that was about well. So now the GSA, they are paying attention to all of this stuff about health and lighting. And they are the government body that manage the government buildings. So I thought, you know, this is even before the pandemic. I reached out to them and we talked about this a lot, and they're definitely going to incorporate this into their requirements for GSA buildings. And, you know, who knows, with the stimulus money, this may, you know, benefit us as designers and architects in terms of, you know, remodeling or such. But I bring this up because they are paying attention to lighting and health at the governmental level. So they did different test cases, and so it's electric lighting, day lighting. So yeah, this is a part of their the Office of Federal High Performance Buildings. So, and they pay attention a lot to the Lighting Research Institute, which is from Rensselaer Polytechnic Institute, which has done a lot of the kind of groundbreaking research about circadian lighting. So next, I'm going to kind of go a little bit outside. I want to talk a little bit about daylighting and maybe some tools that as architects that you already may use, you're curious about using, you want to hire somebody to use or something like that. So daylight modeling. So we also do that as part of our practice. And I'll talk about some of the tools and some example projects here. So basically, you have to know where you are on the planet to do your daylight modeling, your longitude and latitude. And so, yeah, this is just an example of certain sun path diagrams, and you could see there some buildings. You may have seen these. So this is a project we did for a conference center, and this was a little bit unusual because they wanted to use daylight throughout the day, but you have you have the south facing wall, huge wall, and usually these are designed like black box theaters, right? So you control everything with the electric light. You can make it completely dark, but in this case, they didn't want to do that. They wanted the daylight. So we really had to control it. So we did lots of simulations. And in this project, definitely a higher budget project, we got to use electrochromic glass, which it's basically a crystallized glass system that can make it opaque or transparent. It's called electrochromic glass. So instead of shades, right, it's within the glass, these crystals that get electrified and then either go opaque or transparent. So they use it on some big skyscrapers, but we use this glass in the skylight so that we can we can control the glare. And then on the side, we came up with a system of louvers that are solid, that can open and close, but then there's another perforated layer, and these are all automated and there's sensors and such. So we did lots of daylight modeling, and we kind of aggregated, you know, you always take your kind of the March 21st, June 21st, December 21st, you know, the solstice and equinox, etc., to get your kind of baseline. And that was one way to use the software. And I'll get to another software that we started using that would have made this easier, which we didn't have then. But that was for that project. This is a project which is a big redesign of a very famous building, the Crystal Cathedral, designed by Philip Johnson. So it was changed into a Catholic cathedral, and it's open now. It's in California, Orange County. So basically it is a giant glass and truss building. So lots of glare, tons of sunlight, but lots of glare, lots of noise, lots of heat. So those were things that the system had to mitigate. So we worked with the architect and we came up with a system of a daylighting system that's not mechanical, however, takes into account the different way the sun moves across the building at different times of the year. And it was also an electric lighting solution. So we did different modeling and we saw where the light would come in at the most acute angles and cause the most glare and discomfort. And in those areas, we had our louvers kind of closed the most. It's almost like a flower petals. So they're opened up more or less, and you'll see in the next diagram. So these are different kind of quatrefoil louvers, and they are opened or closed at different amounts, right? So again, this had to do with the amount of sun, and they're spread across the entire, on all of the panes of the glass. So, and then within some of the louvers are embedded the electric light. So this system is not only an electric lighting system, but a day lighting system. So it's both. So these are great projects. They don't come around every day, but there's different tools that you can use to kind of do simulations to test out the daylight. And obviously the electric light, which we've been doing, we've always done electric lighting calculations. So spatial daylight autonomy, you'll hear about this in LEED. So it has to do with the percentage of the floor area that receives adequate sunlight. And you also measure ASE, which is having to do, that's kind of with the direct light, glare. So there's certain thresholds that LEED and WELL have about that. So it's not like, okay, pump a lot of daylight into your building, great, but you have to control how it, how the glare is, and there's, again, different ways to do that. So this is a tool that we just started implementing probably about 6 months ago. I think we started playing with it like a year ago, but we just started using it. It's called Diva for Rhino. It's a plugin for Rhino. And you can publish reports of spatial daylight autonomy a lot easier than you would do with kind of these other softwares, which you can use, but then you kind of, it sort of correlates all the data. So if you're interested in your firm to look at spatial daylight autonomy, Diva for Rhino is kind of a great tool. So yeah, those are some of the tools we're using for daylighting. We also use eLume for Revit for our electric lighting. That's just doing all the calculations within Revit. So the last part is just kind of a little bonus about some of my thoughts about light and daylight and skylights. So this idea of a light oasis. So I talked about just before ASE and that kind of sunlight that perhaps could be a glare, a discomfort, and there's certain thresholds. but I believe that there's certain parts of the building that you can have more glare. They're not where people sit at their desk, but certain kind of atriums or gathering spaces that you really see the shaft of light coming in, right? So it's maybe not optimal to sit under and work. However, you perceive the light coming in. And certain times of the year, certain times of the day, there is maybe a large amount of light coming in. And they could even be places that you can go and sit and kind of, when I was talking about this circadian stimulus, so maybe it's too cold to go outside, but you go and you sit under the skylight and you get that circadian stimulus into your eye. So for this project, we consulted by helping to design a skylight system, and underneath this social stair was a gathering space. So we didn't have to light for working, and we had to mitigate glare, but we could still have a pattern. So I kind of call these areas like a light oasis. So those areas in the building, perhaps where you can't reach daylight to all the occupants. However, you provide a space in the building that people can actually go to, right? So I kind of call these light oases. So this was a fun project where we got to design this faceted skylight. And, you know, we could do different modelings to see the pattern. We created animations to show how it moved. So that's kind of a concept, light oasis, which you can use in your buildings. So there's some images there. So anyway, that is the end of my sort of talk in that sense, but I wanted to leave it for any questions. And I guess my biggest takeaway is you don't have to remember all of these certain terms I brought up. However, I wanted to, you know, maybe kind of say, okay, light has a visual aspect to it and a non-visual aspect. So that is kind of, hopefully you've gotten that from this talk, that takeaway. So if anybody has any questions, they can type it into the chat area below, or if yeah, comments or whatever. I know I went through a lot of terms, so perhaps there is kind of a lot to digest, and some of this can be quite technical. And also I have my email address up there, so if you actually want to reach out to me with questions, that's fine too. So I'm open to that. I'm kind of a lighting geek, so I like to kind of talk about these things. And also I have my email address up there. If anybody is interested in me interviewing you about, I'm doing this kind of research about neuroscience and architecture. If anybody has any thoughts about that, and doesn't mind me asking you some questions at another time, send me an email. That would be fun. And okay, so anyway, I want